Uh, the talk is going to be about not so ancient DNA, which basically means modern DNA, but trying to find out things about the past. And this is that was the deal between Eran and me when he invited me. So I would like to basically in this talk, what I would like to do is give kind of an overview of methods for ancestry inference. And we've been working on this in the last 7-8 years. So I'm going to give a few methods, not so technical, but just basically just go through the method that we looked at. And I think that some of these may have applications in ancient DNA. Some of them are already in the working by some groups. And hopefully for the people like Rasmus here that has probably seen a lot of this, there's going to be some new results in the end. Okay, so what is ancestry inference? So what we're trying to do is we're trying to take basically genotypes or sequence data and trying to figure out where the person is from. So let's say this person, I want to say that is from Europe, this one is from Asia, and so on. And I would like to be able to do this within continents and hopefully basically tell someone where they're from, which city they're from. So that would be the goal. And so this is obviously, once you have collected data, this is a problem, a computational or statistical problem that we're trying to solve. So I guess that some of you have seen these kind of plots. This comes out of programs like Structure or Admixture, and there's a few others. And what you see here, this comes from a study in San Francisco for asthma, and these are 90 individuals that are Puerto Ricans. And basically every rectangle is one person, and the three colors correspond to these three populations. So Puerto Ricans come from Europe, Africa, and Native Americans. And you can see here, what you can easily see here is that every person is really different. Okay, so I mean, not all of them, but basically this person here is basically 100% European. This person here is mostly Native American. And so one of the motivations, of course, for finding this kind of ancestry through the genomics is finding out about history. And so if you look at this graph, for instance, there's two populations here, and actually 5 populations, including these 3. So these are the HAPMA populations, so the Europeans, Africans, and Native Americans. And the same here. And then what you see here, there's 2 populations. One of them is Puerto Rican, and the other one is another population in Central America. Does anyone have a guess based on what you see? Central America. Okay, so it's Mexico, the other one. Which one is Mexico and which one is Puerto Rico? Again, based on history. The point is you could look at this and try to find out what the history is, or if you know the history, you can guess which one is which. And what you should see is that here, you basically almost have no Africans. And here you have quite a lot of African ancestry. So Puerto Rico has much more African ancestry compared to Mexico, and that actually fits the history, so that makes sense. So that's basically the motivation, right? You'd be able to look at these kind of figures and make conclusions like we saw in the last talk. So this is another example, again, from Esteban Burchard's lab. What they did is basically look at Puerto Ricans, but across the entire island. And they looked at African ancestry in every place in Puerto Rico, and then they tried to see if it matches what we know about history. So you could see some facts that actually make sense. So for instance, one thing that you could see that there's a high concentration next to sugar mills. Makes sense. There's no correlation to the port, so basically that means that when they came, they just basically took them directly to the sugar mills, and they didn't stop and had kind of camps of slaves next to the ports. And there's negative correlation to the distance from the coast, so basically that means that the Europeans were inland and the Africans were next to the coast. This is another example that's actually from a paper together of our group together with Noah Rosenberg from Stanford and Doron Behar from Rambam. What we did here is we looked at Ashkenazi Jews, and we tried to look at the history of Ashkenazi Jews. And that's just one of the figures that we looked at. That was basically trying to see if there's a relation to the Khazars. And there was a previous paper that said that there is. And we essentially didn't find any relation. You can see here, this is the Ashkenazi Jews over here, and the Caucasus, basically the Khazars are supposed to come from the Caucasus, and these are the Caucasus. So there is a relation, but the relation to the Ashkenazi Jews is not stronger than the relation to the other Jews, for instance, and actually even maybe less so. What you can see here is that the Ashkenazi Jews are very close to the Sephardi Jews, which also makes sense. So again, these are all examples that you could basically look at these kind of figures and try to make inferences about history or have some evidence. The other application of these kind of methods is a medical application. So this is actually something pretty big. I mean, a lot of people are looking at it. So this is just, again, one example where you can look at Native American ancestry in children that have leukemia. You look at the treatment of these children. If they have more than 10% Native American ancestry, then they have 3 times more chance of having a relapse for the treatment. So this came out in this paper here in 2011, and that's just kind of one example where ancestry could be used. They actually couldn't find any specific SNP that basically would predict this. So when you're looking at admixed populations, what you have is a set of 2 or more populations. In this scheme here, we have 2. And after one generation, basically the population has 3 types of people: the people that got 2 red chromosomes, the people that got 2 blue chromosomes, the people that got 1 red and 1 blue chromosome. And after a few generations, because of recombinations, what you have is that every chromosome is a mosaic of red and blue chromosomes. So you don't know what is the red and what is the blue, but this is what happens in practice. That's what you're going to have. And people have been using this fact in order to find associations of regions in the genome to different diseases. And this is called admixture mapping, where basically people look at this kind of information and try to find regions that are, let's say, with more European ancestry when they look at African Americans, for instance. And these are going to be candidates for regions that have a relation to a disease. So this is basically the motivation. And so we've been looking at it again for a few years. And one of the first things that we looked at was looking at these local ancestry. So finding in every position in the genome whether the person is blue or red, basically, whether they're coming from one population or another. And so this is a well-studied problem. A lot of groups try to look at it. When we actually came in, there were already a few methods that try to do this, but it's arguable how accurate it is. And I'll give you an example here. So this is from one of our papers in 2009, where we had 2 methods. One of them we called it WinPop, the other one we called it LAMP. Basically, the difference between them is that WinPop makes more assumptions about the data that we have compared to LAMP, and then it's not surprising that WinPop gets better results. So what you see here, the colors correspond to the accuracy, and every point corresponds to a simulation of an admixed population. Let's say an African and European would be a point here. So something like 95% accuracy, right? But these are all based on simulations. We had other methods that had more complicated or more complex models, hidden Markov models, if you know. And these work better, but they make more assumptions. They basically, for instance, in this case, you make the assumption that you know not only the allele frequency in every position of this population, but you also know of the ancestral population. You also know the correlation between different SNPs in the population, which is a pretty strong assumption. It could hold in some cases, but not always. So I think all of the evaluation of these methods so far has been done using simulations. And a couple of years ago, we decided to actually try to see if we can have a different type of validation. And what we did is we took the asthma data that I showed you before. They have trios, mother, father, and child. And you could give basically these algorithms only the parents, or just give them only the children, and see if they have an agreement. Okay, so in this case, for instance, you know that the child is, let's say, red, red, and then you run it again only on the parents, and you see that the mother is red, blue, and the father is blue, blue. That cannot happen. So you know that there is a mistake. The mistake could be either in the father or in the child, right? So we don't really know, but there must be a mistake here in one of the runs. Okay, so you could now run it and then try to estimate, see what the error rate is. Okay. So this is just a table of a few of the methods that we ran. Two of them are ours. And you can see there's a few things you can see here. First of all, these are the European, Native American, African ancestry all together. And you can see that there's a very high difference between, there's a large difference between, let's say, this method here and the other method. So different methods are going to give you different proportions. Okay? I'm not saying that one of them is better than the other. I can't really tell. But what I can tell is that if I look at the error, this is the mi-length error is basically these errors that we see because we look at the parents and the children. And you can look at the errors and you see that there's a 2.9% error, let's say, for this method here. You have to multiply it by about 3 to get the actual error rate. So it's about 10% error rate. And then some methods have basically about 40% error rate if you look at this measure. Okay, so, but then when you run it with simulations, you don't get 40% error rate. You get much less. So there's an issue with when you look at these methods, you always have to think about what are the underlying assumptions. Okay, because the underlying assumptions can give you results that could be sometimes too optimistic. Okay, so I want to talk a little bit about a different type of methods, that basically methods that give you the global ancestry, so not the local ancestry in every position. So generally, this is the type of method that give you the proportion of the genome of ancestry in the genome in every position. So the general thing that people do, they basically look at every position in the genome. They say, okay, I have an allele frequency for every ancestry. So let's say in the first SNP, I have 30% allele frequency in European, 20% in African, 20% in Asian. And then I look at the second SNP and so on. And then I use basically a likelihood method to try to estimate whether the person is from one population or how much of the genome comes from each population. So this is one type of method. The other type is the continuous type. So basically, you give every individual a point in the genome. So this picture here is from John November's paper with Carlos Bustamante in 2008. And what they have here is a PCA map of 1,300 people. Every point here corresponds to one person, and the colors correspond to the countries. So PCA basically doesn't know, when you give the computer the PCA, it doesn't know where the people are from, but you can actually see that you get something like the map of Europe. It's not exact, but it's pretty close. And so this is something that people are actually using quite a lot, and we've seen it in a few of the previous talks. But there's some limitations for PCA. One of the limitations is that there is no explicit modeling of the fact that they're diploids. Okay, so you're basically summing up the two haplotypes of that person, right? And when you do this, and if you have a person that, let's say, his mother is from Norway and his father is from Spain, you're going to get a point in the middle, right? So that person is going to look like he's coming from the middle. So we actually thought that we wanted to look also at people that are mixed. And in order to do this, we had to come up to think about basically a probabilistic model, a generative model for the genome. Okay, so the way we do this, we assume that you have, when you look at basically one SNP here, let's say that you have a 20% allele frequency in Spain, 50 in Germany, and 80% in Russia, for example, then if you get someone from France, then you expect the allele frequency to be somewhere in the middle. Okay, so that's actually very similar to what PCA, the assumption that PCA makes. So what we do is we assume that this happens for every SNP. Basically, for every SNP, we have a map. And the map basically tells us what's the allele frequency in every position. So let's say this SNP here has a specific map that will have something like 70, 80% allele frequency if you're in England, but maybe 10% if you're in Israel. Okay? And you have a different map for every SNP. You have to train the data so that you know what the maps are. Okay. So we took the same data that I showed you from John November's PCA map. So every individual here, we know where the 4 grandparents are from. So basically, they're coming from one place. And we ran our algorithm basically on it. And what you get in the algorithm, you start with just placing the individuals in random places. And then in every iteration, you learn what the maps are of every SNP. And once you know what the maps are, you basically try to remap the individuals. And so these are the iterations that you see. And you see how after just a few iterations, you get very close to the map of Europe. And we get to about 250 kilometers median error. And we have an even newer method that basically gets to about 200 kilometers, where we actually use the fact that SNPs are correlated to each other if they're close to each other. So going back to mixed ancestry, this method, basically when we published that method, we gave also the results about what happens when you have one person that his mother comes from one place and the father comes from another place. But we want to go back a little bit more. So we recently developed a method that we call it SLAM. It's not published yet, but basically what it does, it tries to give you your ancestors a few generations back. So basically, in theory, it could go back as much as you want, but in practice, because there's less and less data, then you can't really go as much as you want. But it does a pretty good job when you look at just the parents. You want to know, you want to give 1 point for the father and 1 point for the mother. And if you go to the grandparents and you want to give basically 4 points, and you want to go to the grandparents, then you're going to want to give 8 points. So this is, we get about 300 kilometers for parents and about 400 kilometers for grandparents. And then when you go to grandparents, it becomes a little bit less accurate. Okay, so I want to show one example of how can this help in a different setting. We asked ourselves, how can we use basically this kind of method in order to understand who wants to marry who? Okay, and if you think about the ancestry of an individual, let's say if I could tell you the ancestry of the two parents, then I could basically see whether there's a relation between the ancestry of the two parents. And so when you think about mating choices between individuals, between humans, there's a lot of things that could happen, right? Like people basically choose their partners based on education level, based on socioeconomical situation, and so on. And these are all reasons that could basically drive the choice, but we wanted to see if there's more than that. So we developed another method that basically looks at admixed individuals, unlike the previous one that looked at people, let's say, within Europe or within a continent. And here we're saying, let's say that you have an individual that is 50% African, 50% European. Then there could be different ways of explaining the parents, right? One option could be, let's say that the mother is European and the father is African. Another way could be that both the mother and the father are 50%. So we developed a method that basically will tell you whether what is the mother and what is the father. This method can only go 1 generation back. Okay, we still don't know how to do it for more than 1 generation. We validated this method using the trios that I showed you before. So basically, we can look at we can run LAMP or any of or admixture basically, and figure out what's the ancestry of the parents and what's the ancestry of the children. And you see that it's basically on the same line. So we actually have a pretty good estimate of the ancestry of both parents. So we did it for the Latinos. So it's not the example before was for African Americans, but it could be also it also works for Latinos. And then when we looked at the European ancestry in Mexicans and in Puerto Ricans, we see that the European ancestry is basically lies on the line. So if someone is 20% European, they tend to marry someone who's 20% European. If someone is 60% European, they tend to marry someone who's 60% European. Not clear how. We checked, it's not in the slides here, but we checked that it's not explained by education and other socioeconomical parameters that we had. And obviously it depends on this, but it doesn't explain what we see here. This line here that we see that the correlation is so strong, it's not explained by at least the parameters that we looked at. So there's something in there that basically tells someone that if I'm 25% European and 20% Native American, then I'm choosing someone who's kind of like me. And this is the Native American ancestry again. For the African ancestry, it's not as good, but part of the reason is because there's less African ancestry. So it's harder to basically to do that. There's more noise in the estimates. Okay, so I'm going to summarize with just a few points of discussion. So the first thing is, obviously, as you all know, if you look at ancestry inference methods, these could be used to reveal historical patterns, and basically both with ancient DNA and with modern DNA, and obviously with the combination. I would say that you have to kind of be careful, especially when you look at the combination of the two, because you always have to try to understand what are the assumptions that you make, and it's going to be pretty hard to, let's say, simulate ancient DNA data and try to understand what are the effects on what are the artifacts that you have when you apply these methods or other methods to this type of data. So this is something to keep in mind. It's not that you don't want to use any of the methods. You definitely want to use them, but you just have to keep in mind that there could be some artifacts, and just keep thinking about what are the potential artifacts and try to see if you can somehow avoid them. And then the last thing is that if you think about a lot of the studies that look at history based on this kind of plots that I showed you before, and they tell you that, let's say, Ashkenazi Jews came from 800 years ago, like 300 people 800 years ago, and so on. There's a lot of studies like that. They all assume that there is a random mating, and there is assortative mating. Obviously, there's assortative mating by what we showed, and so, for instance, this time span of the mixing should be longer when you think about it. How much longer? That depends on the assortative mating, and it's not clear what to do there. But just again, keep in mind when you think about these kind of problems, and when you read this kind of analysis, then you have to keep in mind the fact that random mating is not true, especially when you look at admixed population. Probably it's also not true in other populations. And therefore, definitely the timing, maybe other things should change in the analysis or in the results. And that's it. I want to thank my collaborators, and thank you for listening.
Thank you, Eran. We have time for a few questions.
Yeah.
In the SLAM method, when you go back 2 generations, you look at the grandparents, do you take pedigree structure into account, or do you assume